1. Frequency modulation results in audio with very different kinds of sounds. 2. The definition of frequency modulation is that a signal is frequency modulated, that is, we find a cosine of a sine. The signal to be modulated has some maximum modulating frequency, FM, so we have to analyze the signal Y, given here. 3. There is a lot of math involving the imaginary number I, which is the square root of -1, and expanding the signs to their Taylor series. The term JNB is a Bessel series. Even though the series are infinite, like the exponent e, cosine, or sine of an angle, or pi, it could be approximated by a number. We usually round to some decimal place as computers have finite accuracy. There is a Bessel series, that is, rounded to a number, for each integer n. The most important result is that now many frequencies result with the form fc plus n times fm, with n being either a positive or negative integer. This results in more frequencies in our resulting signal centered at the carrier frequency. 4. The most important C-sound FM opcode is fossil. Note, there are 6 required parameters and 1 optional parameter. The optional parameter should be left out so it defaults to 0. Also, the KCP term should always be 1, so that the inputs XCAR and XMOD will refer to FC, and FM, the input XAMP, is the amplitude and usually an envelope. The input KNDX is the value, B, in the FM definition. B is called the modulating index, and the larger the index, the more frequencies should be in the resulting signal. One of the important things to note in FM synthesis is that the resulting frequencies should not hit the Nyquist frequency of 22,050 Hz, so all frequencies are correctly mapped and not shifted down. This artifact is called aliasing. Here, we assume the sampling frequency is the usual 44,100 Hz, and thus the Nyquist is half of that. 5. There are 2 examples that we will go into. The first uses a carrier frequency of 2200 Hz, modulating frequency of 10 Hz, and an index of 10. The envelope goes from 0.1 to 0.3 with fade in and fade out at either end. 6. In the next example, a string template is created. There are 3 placeholders representing the carrier frequency, modulating frequency, and modulating index. 7. Now, 150 different but similar instruments are created. The carrier frequency is always 2200 Hz, and the modulating index is always 10. Only the modulating frequency changes from 400 Hz to 251 Hz. Note, in the instrument call an empty string is passed so extra comment are not included on each line in the C-sound file. Now, the comment has been moved outside in a room function call. 8. Finally, a score line is entered for each instrument. Each score line lasts for 0.4 seconds and are called in succession. 9. If you were to look at the C-sound file, it will be over 900 lines. The Python program is only 30 lines. We can make the Python program smaller by removing empty lines, etc. But this results in more confusing code. We only have to type the Python lines correctly rather than typing everything correctly in the C-sound file. This would result in less debugging time. 10. This is the output wave file for a small time duration. The 150 different instruments have output sounds in very different sound color, that is, timbre. 11. You will find additional information at pythonaudio.blogspot.com, including the source code.